Alright, today we're going to discuss on the concept of equilibrium. Alright, we're going to see what equilibrium is and the conditions that are necessary before we can say that a system, a body, an object is in the state of equilibrium. Now I'm going to keep it very basic. So when I think of equilibrium, a word I like to think of is balance. Okay, so this is something you must, have in mind when we're talking about equilibrium. We're talking about balance, whether we're balancing forces, and obviously it's going to be forces, right? Because in the context of what we're talking about, equilibrium here might balance is a very good word, synonymous to equilibrium. So that is what equilibrium. When we say that a system is balanced, there is no net force on the system. Everything has cancelled out, equal to zero. That's what equilibrium is. So let me just give you a visual illustration. Imagine we have, say, a bus. All right, let me just say I have a system. This bus will represent our system. Now, if I apply a force, all right, say I apply a force in this direction. Say I apply a force in this direction. Okay, let's call this F. All right, it can be 5 Newton, 10 Newton, 1000 Newton, as regardless of the magnitude of the force. Now, of course, you know that force is an act that causes a change in position of a body. So the natural reaction, what I'm expecting is that when I apply this force, this box is going to move, right? It's going to move in this direction. There's going to be a displacement. Okay, so we have a net force acting on this box. However, what if I applied an equal amount of force? Okay, what if I applied an equal amount of force in the other direction, the opposite direction? All right, so let me also call this force F, such that F is equal to, all right, surprise, I'm just using, okay, let me just use F1 and F2. All right, let me say that this is F1 and then this is F2. Now you see that I'm applying in opposite direction. Okay, so when we have not put F1, all right, okay, let me just see in terms of F2. When we apply the force F1, assuming there was no force F2 on the other direction, this bus is going to move towards, the left, or the right rather. It's going to move towards the right. But then we're applying another force. It's as if it's a counter force. It's trying to counteract the effect of the first force. All right, now given that these two forces are equal, if we say that F1 is equal to F2, what do you think will happen to the box? Will there be any displacement? Will there be a change? What will happen to this box? What you're going to discover is that this box is not going to move. All right, so it seems as though the definition of force, according to Newton's law of motion, all right, when we talk about the first law, that a body will remain in a state of rest unless it's acted upon by an external force, it seems as though that law is being contradicted. No, what is happening is this body is in a state of equilibrium simply because the sum of the forces acting, all right, because you see that if from this equation now, if I can now say that F1 minus F2 is equal to 0, all right, so the sum of the forces acting on the body is equal to 0. If you sum all of them, it's going to be equal to 0. That's why it's almost as though there is no force acting on the body, because what F1 is doing, F2 is balancing it, right? Keeping the body at rest. So that is what we call equilibrium. So I'm going to go ahead to begin to mention the conditions. We have 3 conditions for equilibrium, and I'm going to deal on 2-dimensional problems. So I'm not going to talk about 3D. I'm going to talk about just the 2 dimensions, that's the X and the Y axis, and then I'm going to include the moment. So what's the first condition? The first condition is just what I've illustrated. These forces are acting in the, if you remember from your Cartesian plane, all right, you have your Cartesian plane. This is the positive Y, this is the negative Y, positive X and negative X. All right, but we're not just interested in the negative and positive, though it matters. All right, when we're talking about force is a vector, so we must make reference to whether it is positive or negative, from our Cartesian convention. But what I'm saying is this force now we have is acting in the X, if you can see, is a horizontal force. So one of the first conditions is that the sum of the forces, all right, in the horizontal direction, sum of the forces in the horizontal direction must be equal to 0, just like I've illustrated. Okay, sum of the forces the horizontal must be equal to 0. I hope this is clear enough. Meaning, another way you can write this in another way. You can simply say that the forces, we're talking about the horizontal, so I think I'll just write horizontal, all right, which I'm representing with x. Another way you can write this is that the forces in the positive x direction, so I'll call it positive x, must be equal to negative x, all right, and we're taking their sum. So, some students like it in this direction where you're going to say, okay, the sum of all the forces in the positive x direction is equal to the sum of all the forces. That thing that looks like E here is the summation sign, just in case you're not aware. So this is the summation sign, all this. It means we're taking the sum of multiple variables or multiple values. So this is the first condition for equilibrium, which you can clearly see, because if they are all equal, the body will not move, right? It will be in equilibrium. So the next one is for vertical. Right? Imagine this same box. All right. Imagine that I have forces acting in the vertical direction. I have a force acting, downwards, and another one acting upwards. And if they are equal, okay, let me call this F3 and F4. So if F3 is equal to F4, notice that they are going to cancel out. Therefore, the body will still not move because the forces acting on it are cancelling out. So therefore, we can say the same thing. Another condition for equilibrium is that some of the vertical components, or rather the vertical forces, must be equal to 0. Another way you can say this is that some of the positive, forces acting in the positive y must be equal to some of the forces acting in the negative y. Okay, they must be equal. And then finally, the last condition is, okay, so say we have forces. Let's say we have a force acting, in this direction, and then let's say I have another force acting in this direction. And remember, if we are taking moments, then we need the point about which we are taking the moment. So let's call this, let me say the length of this is AB. And let's say that we're taking a moment about A. So A is the turning point. Okay? So, of course, if you recall from the previous video, if we take this moment, you see that this first force, let me call this F1, alright? I'm just using F1, F2, and other. About A is going to turn this beam in this direction, alright, which is clockwise. So this is going to have a clockwise moment, right? It's going to tend to turn the meter rule in the clockwise direction, whereas F2 will tend to turn it in the anti-clockwise direction. Okay, so you see that these two forces are, seeking to turn the beam in different direction. Okay, now this meter rule will remain in a state of equilibrium if the sum of, or rather, let me not put sum this time, if the clockwise moment, so we can put it like that, if the clockwise moment is equal to the what? Anti-clockwise moment. Of course, it makes sense. If the amount of force, the amount of moment in the clockwise direction is equal to the amount of moment in the anti-clockwise direction, they're going to cancel each other, and this beam will remain, stable, not moving. All right, so it's going to be in equilibrium. Another way you can write this, to use the summation, we can say that the summation of moment about any point, since we're taking our moment about the point A, I can now say summation of a moment about A, m sub A, must be equal to 0. All right, it must totally cancel. So these are the three conditions for equilibrium. We just want to have, a basic understanding. We have the horizontal, which you can clearly see there. We have the vertical. All right, some of the forces in the vertical must be equal to 0, and then we have some of moments, must be equal to 0. Must be equal to 0. So if you take all this into consideration, just try to digest all of this. It's going to be very easy for you. In the next video, we're going to start calculations on equilibrium. Let's see how we can apply these concepts. Now, the last thing I want to say is, when there are certain assumptions we make, okay, there are certain assumptions we make. So let me not say certain, just few assumptions, which I just want to discuss. One of the assumptions is this: if you have a meter rule. Every time we talk about a meter rule, right? If we have a meter rule, let's say this is a meter rule. First assumption is that if the length of the meter rule is not given, all right, you can always assume it's going to be 100 centimeter, right? Because most meter rules we use in laboratory science laboratories is 100 centimeter length, or 1 meter, right? 100 centimeter is 1 meter. That's the first assumption. Number two is that anytime you're told that is a uniform meter rule, once you hear is a uniform meter rule, or even a uniform rod, uniform anything, once it is uniform, we have what we call the center of gravity, the point, that particular point in the object where its weight is concentrated. So most of its weight is going to act in that point. It's what we call the center of gravity. Now, if it is a uniform rod, the center of gravity is at the center, all right, or midpoint, or midpoint, all right, midpoint is better. So this is where the center of gravity is going to be, meaning if this is a meter rule of 100 centimeter length, the weight of the ruler is going to be acting at the 50 cm mark. So at the 50 cm mark, that's going to be where the weight, which is equal to mg, that's where the weight of the ruler is going to be acting. You don't need to be told. Anytime you hear uniform, rod, uniform rule, uniform whatever, the weight is going to be acting at the midpoint of that object. Please take this into account. All right, so if that is taken, then stay tuned while in the next lesson now I'm going to now we're going to solve, all right, we're going to solve questions. So I want you to participate.